Hello, everyone. In this talk, I will revisit the last level cache hierarchy, which is also called LLC, and make a comparison between conventional shared LLC and die-stacked private LLC. Then, based on the long latency problem when accessing shared read-write data in die-stacked private LLC, we propose one update protocol to solve this problem and also avoid unnecessary updates, which may generate huge traffic. So as we all know, today's processors employ shared LLC. So let's have a quick look about the comparison between conventional shared LLC and private LLC. We can see in shared LLC, when a block is shared, there is only one unique copy of the block located in the LLC, but the block may need to be replicated multiple times into a coarse private LLC. This means that the shared LLC has a higher effective capacity. Secondly, when a cache block is shared, we can easily find the block in the shared LLC. But in the case of private LLC, we may need to go to the remote coarse private LLC to find this data. This means that the access latency for shared data is low in shared LLC. However, if a block is private to a core, then the average latency of a local head is quite low in private LLC organization. The last point is that the shared LLC will cause high thread interference and contention, which is bad for QAs. But in private LLC, there is no interference or contention, which is good for QAs. To summarize, both conventional shared and private LLC have their advantages and drawbacks, but none of them are perfect for today's cache hierarchy. So let's take a quick look into conventional shared LLC. In the left picture, it's basically planar based, and the LLC is shared by ops cores. And previous work also proposed next-generation LLCs. We refer to NG-LLCs in this talk. It can be found in the right picture. Basically, it uses multiple layers DRAM stack on top of a CPU die and vertically partitioned into slices called vaults. And the vaults are private to the core. So it uses die-stacked DRAM to provide large LLC capacity, and the vertical interconnect can provide fast vault access. Finally, the private organization ensures good performance isolation. So to summarize, NG-LLCs can provide large capacity and also fast cache access. So let's have a look into the performance impact of different LLC organizations. We consider two LLC capacity, 32 megabytes for conventional LLC, which can be shared or private, and we use die-stacked DRAM with 8 gigabytes in total, and which means 512 megabytes per core. And you can see this one is a conventional shared LLC, and this one is the NG-LLCs. For the fairest comparison, we augment the 32 megabytes LLC with an 8 gigabytes unpackaged DRAM cache, which is similar to Intel's Light Landing. And we evaluate them on PACT', and the results can be found in the figure. And the first bar shows is the conventional shared LLC, and the last bar shows the result of the NG-LLCs. So from this figure, we can see the shared LLC outperforms private on a conventional LLC, and the private outperforms shared on die-stacked DRAM cache LLC. And we can also see the NG-LLCs is better than the conventional shared LLC by 16%. So to summarize, if we can have a larger per core LLC capacity with fast accesses, then NG-LLC are the best choice. So after a comparison between different LLCs, let's take a look at how accessing shared read-write data works in both shared LLC and NG-LLCs. In shared LLC, if a core issue a read request, and then it means in its L1, and also then it means in L2, and finally it finds the data block in the shared LLC. So basically, it's quick and direct. Since the directory is co-located with LLC, there is no additional accesses, which means we can quickly get the shared data block. So to summarize here, the access to the shared read-write data is quick in shared LLC. And let's take another look at on the case in NG-LLCs. Please remember, NG-LLC is a private cache organization. Think about the same case. A core issues a read request, it misses in the L1 and miss in L2, and then it misses in the local LLC, and which means it will look up the directory. Then the directory denotes that you may get a remote hit in a remote host LLC. So this is the worst case, and since the directory is separate from LLC, which means that there are multiple DRAM access and log traverses. So which means the access to shared read-write data is extremely slow in NG-LLCs. To summarize here, because we have many indirections, which will make the accessing shared read-write data extremely slow in NG-LLCs. Since we know accessing shared read-write data is slow in NG-LLCs, we would like to study the distribution of the LLC access for 3 access classes. They are private, shared read-only, and shared read-write. From the characterization result, we can see most of the LLC fall into private, which is good for NG-LLCs, but there is still nearly 10% of the access fall into shared read-write data. And please remember how slow to get the read-write data in NG-LLCs. So there are multiple DRAM access and log traverse. So we then study the performance impact of shared read-write data. We study the performance gain from avoiding access latency to shared read-write data from the remote world. And the potential performance improvement is 14.5 for shared read-write data. So we can summarize here, there is a significant performance opportunity to eliminate remote reads to shared read-write data. And then let's take a look into how coherence protocols treat the read-write data. So we all know in today's system, write-invalidated protocols are widely used. It guarantees coherence by invalidating all of the shares of a cache block before write, but the drawback is that it exposes remote access latency for shared read-write data. And another kind of protocol is write-update protocol. In write-update protocols, the data is pushed to the potential readers after the write, which means it can hide the remote access latency for the shared read-write data. But the drawback is that we will keep sending the update if the cache block is not consumed by any reader. So to summarize here, we can see both invalidate and update protocols treat shared read-write data differently. Then we use this table to show the comparison between invalidate and update protocol. In invalidate protocol, the access to shared read-write data is slow, but in update protocol is quick. And the coherence misses is high in invalidate protocols, but the update protocols can eliminate the coherence misses. And the last point is that the invalidate protocol generates no traffic on log, and in contrast, the amount of traffic is huge on log in update protocols because of the unnecessary updates. So to summarize here, both invalidate and update protocols have their drawbacks. So since both invalidate and update protocols are not perfect, there are many proposals about adaptive protocols which combine the advantage of both invalidate and update protocols. And I will introduce 2 of them. The first one is CU, which is a competitive update. In CU, there is a counter associated with each cache block and set to a given threshold when at the initialization stage. And each time when sending the updates, the counter is decremented. And when the counter reaches 0, CU will switch to invalidate rather than update. And another method is write grouping, which we call WG in this paper. It uses write buffer and can combine multiple writes to the same cache block into a single update. And we also have a timer here to indicate when to send the update. So to summarize here, adaptive protocols can combine the advantages of both invalidate and update protocols. And we then take a study comparing the existing protocols. All results are normalized to the baseline right up invalidate. And from the results, we can see pure updating protocol W hurts the performance, and both WG and CU improve performance over the baseline WI. But all of the existing protocols fall short of ideal improvement. So we know that updating protocols have the potential to eliminate the latency of a read for shared read-write data. But the drawback is that it generates excess traffic. So our goal is to precisely identify when to send the update. So based on this motivation, we make a critical insight is that the number of writes without an intervening read tends to be stable. And we can see the result in this figure. Basically, we can see there is a 70% of the chance that the number of writes in current write-read iteration is same as the last one. So based on this observation, we propose one updated protocol. The main idea is to leverage the write scalability by recording the previously observed number of writes for shared read-write cache block without an intervening reading, and then updating shares of the block only after the expected number of writes. There are two benefits of doing so. The first benefit is that one update protocol can eliminate the read latency for the shared read-write data by pushing data in advance. And another benefit is that one update protocol can avoid extra traffic by just sending update once. So we can summarize here, one update protocol performs at most one update during each write-read iteration. So let's take a look into the protocol details. So basically, we have a write counter. It's used to record the number of times that a shared block is modified before intervening read. For example, if there is 5 writes before read, then the counter value is 5. And we also have a decremental counter. And at the beginning, it will be initialized to the value in the write counter. And each time there is a write, the value in the counter is decremented. And at the same time, we'll compare the value with 1. If it's above 1, we will perform the invalidate. And if it's equal to 1, we will send an update to all of the potential shares which are recorded in the directory. So if there is a read and the bunch of writes, we will reset the value in the decremental counter to the write counter. And this indicates a new write-read iteration. Then let's look into the protocol overheads. Basically, we just need 7 extra metadata bits per cache block. 1 bit for read flag indicate whether a call has read the block, and the 3 bits for the write count is a static counter that tracks the number of writes, and the 3 bits for writes until updates. And the best this has been detailed in the previous slides. And one update protocol is integrated with the baseline Morrissey invalidated protocol. And it means there is no new coherence message types and also no changes to the directory. So please see the paper for design details. And also, one update protocol is formally verified, and the details can be also found in the paper. So to summarize here, one update protocol is simple and with minimal overheads. So let's have a look into the evaluation method. Basically, we have a 16-core setup with private L1, L2. And for conventional LLC, we use 32 megabytes new car. And for NG-LLCs, we have 512 megabytes capacity per core. And for coherence protocols, we evaluate the baseline, Morrissey write invalidate, CU, and the proposed update. So we firstly evaluate the performance on parsec. From the results, we can see one update protocol outperforms CU on overclock by 4% on average, and it also improves performance by 8% over the baseline write invalidate. To summarize here, one update protocol can significantly improve performance. And then let's take a look at the evaluation of log traffic. So basically, one update only generates 9.5% more traffic than the baseline WI, but at the same time, it generates 20% less traffic than CU. To summarize, one update creates considerably less traffic than CU. So in conclusion, NG-LLCs offers advantages over today's shared LLC, such as large capacity with fast vault access, but it suffers from slow intercore reads for shared read-write data. So we propose one update protocol to solve this problem. It exploits write scalability to hide the read latency to share read-write data with only a single update, and it's also very easy to implement. And after evaluation, one update protocol can improve performance by 8% over write invalidate protocol, and at the same time with low log traffic overhead. So you can find more results in the paper, including performance in shared LLC, performance on Splash, and also the reduction in coherence misses. So that's all. Thank you.